Rose was going to. Yes, we are.
Excellent. Thank you very much. And hello and welcome. Hey, I'm Nick Owen. I've been with SAE as a volunteer for over 10 years. And in the last 5 years, I've been the autonomous subdivision team leader. I also, as my day job, I lead a group of 8 electrical, mechanical, and mechatronic engineers designing prototypes for Defence Science and Technology Group, part of Defence and the Australian Government. So I would like to take the opportunity today to talk about systems engineering and specifically how and what it means to formula teams. I really see this idea of systems engineering as setting up a team to win. And I don't necessarily mean win trophies. I mean by winning at understanding a skill that's used in industry and is fundamental for future and engineers of today. So it's something that we use a lot in industry, and not just in defense, but in automotive and also other sectors such as manufacturing. And it's applicable not just right with formula, but I want you to understand as a group that these are concepts that are lifelong concepts. It's not like I know those terms now. That's enough. These are elements or concepts that we really want you to start thinking about if you're not already thinking about them, and how you can apply them right now in a very practical way. All right, so what is model-based systems engineering? So you may have heard the terms MBSE, model-based systems engineering, and it really kicked off around the 1940s, but more into the 50s and 60s, coming out of NASA. And, you can read the text there. It's a multidisciplinary approach for designing, realization, and technical management. Now, that sounds a lot like FSAE teams, right? Where you might have mechanical, electrical, and everything in between, including management elements. And you're sharing a common goal of building a vehicle. So it sounds like model-based systems engineering could be a good fit for your teams. The elements may include hardware, software, equipment, facilities, personal processes, and procedures. So it's not just about building the part or realizing the vehicle has to have 4 wheels. It's about the whole process of how you think about design. It's not just, hey, we need an upright, so we're going to build an upright. It's about thinking about, well, what does the upright need to do? What systems does it need to connect to? And starting to think about the systems of the systems. Now, these are key phrases within the systems engineering world. And also setting baselines. Baselines are really important. So when a team comes to competition and they're bringing their vehicle and they set the design goal to have 4 outboard motors, if it's an EV, but they've never done it before. In fact, the year previously, they probably would have been a combustion team. Is that a good idea? When their goal, their objective should have been just to participate in the dynamic events. But they've gone and over-engineered the solution and may not do well. They may not even end up on track. So this is where goal setting and requirements become really important. So the V model, how do we put all this into context with the V model? Well, success means setting good requirements. A project can be the difference between success and failure in a project, no matter the cost, is all about how it is set up at the start of the project. If you want to engineer to win or engineer to succeed in life, you have to have good requirements. What makes a good requirement is a set of system shell statements. So a system shell statement, I'll give you an example. The system shall have, or the vehicle shall have 4 wheels, okay? Well, why does that matter? Well, the vehicle has to transmit torque in order to go forward, all right? But are there any other parameters around that? Well, the wheels can't be enclosed. So that's another requirement. A good requirement is all about the single statement. So you could say the example of a bad requirement, like The vehicle shall have 4 wheels, and all those wheels shall be covered, and the wheels should have a connection point to the upright. That's a lot to unpack and very hard potentially to verify. Whereas you could just say the system or the vehicle shall have 4 wheels. The vehicle shall have wheel lugs. The vehicle should have a method of connecting the wheel to the upright. And they become very easily able to unpack, also very easy to break down into discrete work packages for engineers or your students. And more importantly, they're verifiable, right? So let's talk back and look at the V diagram that you will have on your screen. The V is the process of design, where when we go down the V, where we go from the concepts of operations, system requirements, high-level design, detailed design, then we go back up the V, where we start thinking about the testing. So down the V is all about design. Up the V is all about test and verification. Now, I know a lot of teams are under resource constraints, whether that be time. Finding the time is very hard, money, and experience. So quite often we see teams that may come to the competition a little bit underprepared, where they've spent all year or maybe even multiple years designing a vehicle, but haven't had the opportunity to test. Now, designing to win means that you factor in the test effort and what's required to reach your goal or verify against your requirement in this case. So if you have a goal or a requirement that the vehicle shall compete in all dynamic events, right? Now, in order to achieve that requirement, you have to go through your detailed design goals. That means if you're following a systems engineering process, you have to set your requirements. You may have a requirements review before you even think about doing design. That means hands off keys, no CAD until you have your requirements set. And then once you have your requirements, you design to your requirements and goals. So, but you don't just go forth and design and then go straight into production, because that's crazy. That's not how we do things in the industry. We go through a methodical way of approaching design. So when myself and my team goes through a design process in following the systems engineering V model, we first design to about 75%. So that means we design up to the preliminary design review, the PDR, right? And this is a group design. So for instance, we might get a client stakeholder involved. And at this stage, we may have constructed some kind of prototype, but we may not have gone all the way there. So the goal with a PDR is to try and get there as quickly as possible without spending a lot of time and resource. So this is where you do a fair bit of CAD work, right? But you're not yet manufacturing the final product. So at the PDR point, this is where you have the group review and say, okay, does it meet the requirements? So you always trace back to your requirements. Yes, no. Does the form fit the function? And is the function good for the form? And then you also start to consider, well, how will we make it? Like, what processes will be involved? What kind of time is required? And potentially, you'll be planning for the future. So just say you get through your PDR phase, designing your upright, for instance. You've done all the design work, but you may spend that last 15% doing optimization, right? Or some additional FEA work that you knew was going to take a lot of time. Your design was okay, but you just wanted to make sure it's the best possible thing. So then you go to your CDR, your comprehensive design review, and then you make sure that you have, at that point, all your manufacturing drawings done. They're being reviewed. Is it feasible for the production methods that you've chosen? And have you got the resources to do them? For instance, not everything has to be CNC machined. Some things could be just laser cut and folded, and still achieve the same form, within moderation. right? So you factor in at the CDR point how the thing's going to be made. Whereas at the PDR stage, you may just be using block models and you haven't really considered as much as you would in the CDR phase of that final form. So once you've finished or exit out of your CDR phase, you can set baselines or product baselines. So once you've got your product baseline, you're sending it off a manufacturer, or maybe you're making it yourself and machining it or cutting it or drilling it in-house. You know, that means you're all on the drill, you're on the lathe, you're on the mill, or you're on the soldering iron, soldering up your electronics, because this is not just a mechanical process. This can be applied to any form of engineering, right? But what you want to do after you've manufactured something, right, is that you want to make sure that it still meets your initial requirements, and also that what you've made matches your drawings. So often you'll find, especially when you're making something for the first time, that design changes because for instance, you're in the CAD file, you've set a chamfer that's impossible to do with the manufacturing process you've done. Well, you didn't catch it in the CDR, but you've found out when you've looked at the part that you've made, some feature or form of it wasn't quite right. Well, that's okay. You've set a baseline. Well, you can just now update your baseline by ensuring that you change your manufacturing drawings. So, but you see, following the process is ensuring control and configuration management. So this ensures that not only that your end product is meeting the initial requirement, but it's also repeatable. So just say you've got a lot of people in your team in the current year graduate, right? And they obviously go off and design the next year's vehicle, but they want to use some parts from the previous years. Well, you know that the baseline's been set because you've kept control of that configuration, and there's no reason why they couldn't use that. I mean, of course, there could be some kind of points or, you know, something involved with the competition why you wouldn't or why you should, but at least you know within your team, we've kept control of that configuration baseline. And that's a really important element of systems engineering. So we've covered baselining and we've covered configuration control. The next thing I want to talk about is testing. So you can set all the requirements in the world and you can go through all the design reviews, but does it work? Well, how do you find out if something works? Well, you've got to test it. So this is where we go back up the V, integration and recomposition, right? So there's two main forms of verification or testing that we do. That one's called verification and one's called validation. So the verification could be the desktop kind of test that you can do with standard tools like measurement items like calipers, verniers, that kind of thing. And you say, okay, I've designed this circuit board or I've designed this upright to be this mechanical dimension. Is it that? Yes, no. Okay, does my circuit board power on and does it flash a light because it might be part of a T-cell circuit? Yes, it does. But how do we know that that same device, part or component will still work once the vehicle has done 20 laps of the test track? Well, you don't because you haven't yet tested it. So having the ability to test something on gives you confidence that it meets the requirement throughout its life cycle, right? Now, to say, okay, you may say, well, we won't actually have our vehicle together right until a week before or even at competition. That's a reality. We've seen it many times before. Well, that's okay. You can think outside the box and say, how can I do validation testing in other ways? Well, I'm sure a lot of people have vehicles, right? Or their own personal vehicles, or they can borrow their parents or whatnot. But that's a vehicle that experiences shock and vibration. So what happens if you put that part on your vehicle, your test mule or test rig, and you drove it around the block 50 times, for instance? Now, it's not always feasible with certain mechanical parts, but there's certain things or certain items that you could do that on. But it's to think about the testing, and that testing should be part of your design phase. because only after something has been thoroughly tested can you have the confidence that it's not going to break, it's not going to fail, and it meets your goal. And if that goal is to compete in every dynamic event, the more testing you do, the more confidence you can have going into those events that you're going to get through them. And guess what? If you get through all the dynamic events, you're going to get a lot of points. And a lot of points is good for morale. It's good for the competition. It's good for you. But also, you've done something right because you've done all those good things in system engineering to mean that you've got through that. So that's what going up the V means for me, and in context for formula students and young engineers and senior engineers alike. So how can we use it formally? Like, is there research papers? Is there standards? Where can I get more information about systems engineering? Well, one of them is books. So there's Applied Systems Engineering. I don't know if you can see this book. This is a really great resource. It's by Ryan Falconbridge and Ian Falconbridge and Mike Ryan, Dr. Mike Ryan. It's a great resource. It's pretty military specific, but it's very good in terms of breaking down the process and going into detail between different systems engineering phases. Another great resource, unfortunately, it's behind a paywall, but it's very specific to automotive, is SAE 1001, which is the automotive version or automotive specific version interpretation of model-based systems engineering. So this is a website screenshot of the US SAE international website, and you can see it's $187. But you might be able to access this standard through your university's libraries or technical resources. But I've read it, it's good. Another interesting thing is research papers. Now, I'm not just saying this because I'm a big advocate for systems engineering, but I've also done a little bit of a literature review, and I found that systems engineering has been used by multiple SAE teams or FSAE teams throughout the world. So this is a particular paper that I found that's very scholarly, and it's an implementation of systems engineering by a university in Hungary, for instance. And I guarantee if you search for this particular paper or anything with keywords, systems engineering, FSAE, race car, papers like this will appear if you go through your university libraries or where you get your academic scholarly articles. And what's interesting is that this team probably didn't do as well in the dynamic events, but they did really well through design because they were able to demonstrate their design approach. And I know our local design judges gobble this stuff up because they're all about processes. They're all about repeatability. And they're not afraid or strangers to prototypes or mass production in any means. Most of the judges at competition are people from industry that are actively working in the field. So if we're using this and you're using this, we're speaking the same language. And we can see that teams have used this already. So my kind of mantra for this is prior preparation prevents poor performance, right? So these are sort of some of my goals in terms of systems engineering for teams. And if I was in your position now as students developing a race car in teams, I would say establish your goals. If you haven't already got them, now's a better time than any to create goals. Break your car down into systems, black boxes, systems and systems, and have an owner. So have a student that can tell me everything about that black box, whether it be a T-cell or upright or steering component. Like, you should have someone on your team, if during scrutineering or design or at any time during the competition weekend, they can tell you absolutely everything about that component. Define what each system does. Give it a functional description. Allocate it a baseline. Define the interfaces between systems. Now, this is very, it can get a little bit hairy, particularly when you've got a mechanical engineering student and electrical engineering year 8. we're not doing the same degree. We don't speak the same language, but in fact, you do. You speak the language of engineering, and like good engineers, you've got to find a way to interface, just like good components. Mechanical has to integrate with electrical, else it doesn't work. They're just two independent systems. But in systems engineering, we talk about systems and systems to make the full system. Gets a bit confusing with systems, but stay with me. Set deadlines for reviews. So and stick to them. Particularly in the early phase. If you, there's a thing saying first time to failure. If you reduce that time, then your time to success is shorter. So if you set a short PDR period, then you can get through it. And then you can go and reach a CDR period, and then you're ready for your technical readiness review. Be okay. Assign people to work on the systems or the black box or whatever it is. Assign them, right? And then track their progress through the process. So this is where tools and Kanban boards can be really, really helpful. Regularly review your systems internally to ensure that they comply with the functional description. So this is really good, particularly if you have junior team members and senior team members. I would say get the senior team members to review the work of the junior members, right? And create an environment that's safe and nurturing, because that's what we do in industry. We don't want to be assholes, pardon the French, but we also want to be critical to ensure that we all grow together and we create quality work. Regularly review the systems to make sure that they work together and the interfaces. So if you've got two totally different systems, but they share an interface, get the designers in the same room, right? And I'm not just talking over Teams or WebEx or whatever online video shit. Physically get them in the room and get them to describe how those two systems are going to talk together, right? Pre-plan how you're going to test your system with verification. So do that as early as possible in your design, even maybe as soon as the PDR, and plan how you're going to test the car as a whole system. That's the validation. So I did talk a little bit about Kanbaning boards. So this is the example of an analog Kanbaning board. So you don't necessarily even need software. We've broken tasks into post-it notes, and we've been able to track the post-it notes. And this is on a project of the National Bureau of Meteorology. But there's also other tools that you can use, such as Jira, Microsoft Planner, Microsoft Project. Now, interesting note, Atlassian offers teams free or sponsored license seats to use Jira and Confluence. So if you're not already on those tools, I would strongly recommend that you get in contact or sign up to Jira and start using its Kanban board features. Because, yeah, they're used in industry, and it also helps you manage that process through your design and into validation and verification. So good work, Curtin. So I'm going to pass you on to Graham Holmes now, and I think he's going to talk about some practical hard facts about building, designing, and just going through the whole process of being in the Formula team. So Graham, would you like to take it away?
Thanks, Nick. If I go into share, I can pick up the slides from my screen, I guess.
I'm happy just to keep the slides going. And
there's only two anyway, yeah. So that's fine. Yeah. Okay, let's do that. All right. Well, thank you, Nick. For those who aren't particularly aware of me, I know nothing about FSAE as a student. I don't really have much interest in cars anyway, despite what a lot of people think. But I was the professor of electrical engineering at RMIT for 10 years before I finally so-called retired. And during that time, I was the academic mentor for the FSAE electrical team during about 8 years as we took it over. And I've stayed connected with the team thereafter to help them out. So I have a great deal of experience with watching teams attempting to produce electrical cars rather than mechanical cars, because I got involved with it at the very early stages where EVs were just coming on board. And the primary goal for an EV in those days was to actually run. let alone complete every event. And I remember vividly the time that an EV actually completed an endurance and then got round faster than a petrol car. And the guy who was commentating, he nearly went berserk. He said, "There's an EV car that's faster than a petrol car." And I thought, yeah, well, about time too. So that's my background. And so the comments I want to make are, well, not about the hard facts, but the reality of what you're trying to do is the way I would describe it, because it's a tough gig. Now, a year is a very short amount of time. And particularly if it's your first or early times building an electrical car rather than a mechanical car. One of the things about this system engineering approach, which, Nick, I don't fully agree with, in the sense that systems engineering is important, but there is a primary difference between an electrical design development system and a mechanical design development system that I've seen over the years that I think is absolutely critical. And that's to do with the timelines. When you build something mechanically, you design it, you have it manufactured. As far as I can see, you put it together. And then if it isn't quite right, you can tinker it. You can change it a little bit. You can rework some parts. You can actually recover your mechanical design issues in a relatively short time. Electrical systems are completely different. They have a long construction time by the time you make a printed circuit board, load it and test it. And so your opportunity to do that even twice, let alone 3 times in 1 year, is almost impossible. So that means that you get really one shot at design and manufacture. Well, actually, sorry, that's not what I meant to say. You get one shot at manufacture. So what you need to make sure is that your design is sufficiently robust that when you come to manufacture, it'll work. And you don't get caught with any unexpected problems, because by the time you run another printed circuit board and run it back through, you just won't get it to work. So electrical and mechanical are quite different in the way that they seem to be constructed, and both sides need to appreciate that. Now, one of the problems that I've seen over the years is the mechanical people on the team keep saying, well, come on, the electrical doesn't seem to be doing anything because it looks like nothing's happening. And then all of a sudden you make all the parts and it comes together and hopefully it works. Then you can turn around and say, right, where's the car? We're ready to run. And the mechanical people say, oh, well, we haven't quite got the wheels on yet. We haven't quite got the brakes on yet. We're going to do that next week. We're still putting it together. Completely different context in how you go about it. And both sides need to be aware of that. The car must run before it can be optimized. Well, I go even stronger. The car has to run. In other words, you get nowhere if you built this wonderfully complicated car and it doesn't work. So if you've got a car that works, you will do better than a very clever car that doesn't work. So the analogy there of designing a lightweight pedal box is useless if the car doesn't run. True? Let me go another way. It's absolutely pointless to design the latest bee's knees electrical microprocessor-driven CAN communication system if it doesn't work. And there was one team that spectacularly some years ago had their whole electronics run by CAN communication between multiple microprocessors, and they hadn't actually got it together on the car. And the first time they turned it on, the inverters caused so much noise that the entire communication shut down and they had no car. So a highly sophisticated, complicated electronic design, very clever, didn't work. So you need to keep in mind that the more sophisticated you make it, the more probability there is that it's going to misbehave in some way. There's a very old analogy from the US Army called KISS, keep it simple, stupid. And absolutely true here. For example, something as simple as the safety shutdown circuit. Sure, you can add in some electronics if you really feel inclined, and you can try and put a switch in, although a bit of semiconductor switch, although probably we won't like that. But what's wrong with a relay? A relay is a really nice, simple bit of tried and true mechanical circuitry. And I use the word mechanical because it is. It's simple circuitry. It doesn't require software. It'll probably work. Now, it means the people who want to sit there programming microcontrollers, they won't be able to contribute to that bit of the circuit. That's true, but it will work. Timeline. If you're not running the car in August, you're late. Now, I know that sounds harsh because we're nearly at August. So anyone whose car is not about ready to run together, you're late. What does that mean? It doesn't mean you won't make the competition. It means you'll be cutting corners. You'll be cutting corners, still trying to build it. You won't be testing it properly. You will be struggling to put it together. As Nick said, the number of teams that have put their cars together in the last week of October or November or the week before the competition or at the competition tear out to try and make it ready for operation, assuming they get through scrutineering, and the thing falls over and doesn't work at the first lap of endurance. And that's because you haven't tested, you haven't got it to work. So that's a timeline. Now, it's too late for that timeline to be changed for this year. So all you can do is pick up as best you can. But for next year, you need to keep that in mind. Everyone always has a timeline at the start of the year that comfortably has the car testing in August. It's very confusing, therefore, why most teams aren't testing in August. And usually the reason would be that the timelines, the checks, the reviews, they slip. Oh, we're not quite ready now. Oh, we haven't quite got ready to it next year. Oh, we can't get this piece built because we didn't actually ask the manufacturer, could he build it in one day? Well, actually, if you talk to most manufacturers and they're being nice to you, they'll struggle to build it in 4 weeks, if you're lucky. So you have to factor that sort of time scale in. And everyone comes up with this wonderfully optimistic timeline, doesn't have any checks in it, doesn't have any slack in it, and then it starts to drag. And it happens every year, year after year after year. Be nice to find the team that actually does manage to keep to a timeline. And I do understand how hard it is because you do have to allow for things going off the rails and coming back at it. Now, one of the ways that you can deal with these problems, and again, it comes back to electrical, is early testing. Now, you might say, I just said before that you can't test an electrical system because you've got to build it and it doesn't get built until towards the end of the car coming together. And that's absolutely true. But I've been the senior design engineer with a small development company for about 25 years now. And every time we get a new project, the very first question I ask my engineers is, what don't we know? In other words, what have we not done before? And if we haven't done something before, we will make a prototype of that part. So we will test it out with a bit of circuitry, which is to be thrown out once it works. But we will build ourselves a test system. And so, for example, if you want to build a new microprocessor system to control the whole car, how are you going to firstly verify that you can program it? And how are you going to check that it is robust? Well, maybe the answer is you go out and buy yourself a development board. You put some dummy inputs in it so that you can get it programmed and running. You can even get some software running 6 months before the car is put together. So you've got that under your belt and you know how to do it. So when you come to put the full car together, you're not really doing design anymore. You're just step and repeating what you've done before. So testing of an electrical system, in fact, breaks up into 2 parts. An initial prototype testing of something that might not look like anything like the real car, and then the manufacturing of the real car system, which has exactly the same heart, even though it might not look so simple, might not look the same. Remember, another major difference between electrical and mechanical systems is when you have a mechanical system unsatisfactory, mostly it degrades the car, it doesn't stop the car. Now, there are spectacular differences. You can break a tie rod and the wheel comes off the car, and that's pretty spectacular. But in general, mechanical problems degrade, they don't stop the car. Electrically, a simple wire connection will stop the car. So you can have the best car and everything's tested and you just didn't manufacture the wires properly, and you didn't know that because you only put the wires together in the last week of November, and then that stops the car. And you might think I'm being harsh about it, but let me give you a war story. Some years ago, probably 10 years ago now, we had a team. It was a good team, and the car was doing very well and it had properly run. And everything was fine, got through scrutineering, got through all the Saturday dynamic events. Everyone was looking forward to endurance. And I turned up Sunday morning and the faces hit the ground. The car had stopped. It wasn't running anymore. And they were running around like chickens with a head cut off. So, okay, management 101. Everyone out of the test bay, everyone out of the pit, only 2 people, plus me. First question I said, what did you guys change from yesterday to today? Oh, all we did was remake one of the power connections. It's a simple wire. We just crimped a new lead on. We knew how to do that. We've done it multiple times. Okay, fine. Worked our way through it. Said, that connector is no longer making connection. You sure you knew what you were doing? And why did you touch it Saturday evening? Anyway, long story short, we pulled the connector apart and discovered that they'd bent the high current connector in re-crimping it, and it no longer made contact. And so we hit it with a hammer, straightened it out, plugged it back in, and out they went and completed endurance. Now, lesson from that is, firstly, don't change the car when it's running. And secondly, when something goes really wrong, there's a management problem as well as a technical problem for everyone to clear out and cool heads to try and solve it. And so management is as much a problem as the actual manufacturing. Simple things stop a car electrically. Even for petrol cars, by the way, many petrol cars stop because of electrical failures. It's just that the electrical part of a petrol car is relatively small and mostly it works. But, there are petrol cars that have been unable to start because they probably didn't properly size the battery and the battery got flat. And that happens right in the middle of endurance, and that's that. Other things, avoid feature creep. Well, come back to what I said before. Don't build your electronics with high sophistication, heads-up displays, traction control, torque vectoring, tyre temperature monitoring. They're wonderful things to do. Everyone's really keen to work on the latest fancy ideas. Firstly, do they help the car run? And secondly, if you get it wrong, will they stop the car? And the answer to the first question is probably no. And the answer to the second question is probably yes. One of the years, and I do confess that I lose track of them because they blur between each other, but I can remember one year there was a student who was trying to get the drive running properly with the engine, the motor. I'd finally got them to accept the fact that they needed to test the motor on a dyno test bed rather than in the car. It's a lot simpler on a dyno test bed, on a dyno. But anyway, and he was programming it. It was running okay. And I said, well, that'll do. Let's put it in the car and get going. Oh, no, I want to optimize it a bit more. Fine. How long is it going to take you to optimize the programming? Oh, about a month. Right. How's that going to help the car when you're already running 2 months behind schedule? Oh, but it'll get us faster. And my comment was, it won't get you faster if you don't actually have a car at the competition. And guess what? They didn't have a car that year. It didn't run. So there's another illustration of feature creep and chasing the best. It just doesn't work, mostly. Couple of other issues before I'll pick up the 2 points here. There's another major difference. It's for years now that I've been telling the teams that there's a huge difference between mechanical and electrical in the way you go about the process, and both sides need to be aware of the other. But there's this third element here too, which is often also dismissed, and that is software. Most of the electrical systems are running on software. And the student ability to write robust software is not very strong. But that doesn't stop them writing complicated, high complexity code and confidently saying, it'll be fine, testing it sort of out on the track and the car stops. Now, there's something really disconcerting when you've been writing software and everything appears to be working in the lab, and then you take it out on the track and the car stops. And here's the first disconcerting thing. Why did it stop? Now just think for a moment. Everyone's clustered around watching this car take out comfortably on the track, and then it stops. How do you find out why it stopped? Well, you'd like to think about that at the start, not at the end, because I can tell you if you try and think about it at the end, you won't have a clue. And then you'll have everyone coming up with all sorts of arguments as to why the car stopped, everyone wanting to run off with this, that, and the other, and they're all probably wrong. So what does that mean? It means put logging in. It means put in some way of checking what the car is doing at the point where it stops doing it. And make that logging simple and useful. One of the things that we do with my company is we use SparkFuns. Now, what's a SparkFun? A SparkFun is a really nice bit of technology that listens in on an RS-232 serial port. So we just routinely send out text and it gets swallowed up by the SparkFun. And then if anything happens, you just take out the SD card, have a look at the text file, and it says, this is what happened at the point where it failed. It's simple, it's robust, and it works absolutely reliably. In fact, I use exactly the same thing on the energy meters. So that's a good logging technology. The RMIT team for a couple of years now has been running a CAN logger where they try and log off the CAN communication, which is a perfectly fine bit of exotic technology. The trouble is it requires all the CAN communications to be working reliably. So if the CAN communication stops working reliably, you've got no logging. And that really is a bit of a problem, because if the CAN communication stops logging, running, that could be because of a complicated problem or a simple problem. They just don't know. So you need to be planning and thinking about these things all the way through. It's the mundane business that makes the car run. The car will stop if you do anything wrong electrically. It won't degrade. Chances are it will stop. So you need to recognize that and do something about it. Now, the last 2 points there, consider the learning outcomes. Well, if you don't have a team who's realistically able to write software, use last year's software. But make sure that somebody knows enough to be able to use last year's software and work with it. If you don't have somebody who can lay out really exotic printed circuit boards, maybe you just live with last year's printed circuit board, even if it's not the latest microprocessor controller. The learning outcome for the team members, some team members want to use the latest, newest, brightest, best stuff, but that's not necessarily going to help build a car. Lloyd says, buy something yourself. Don't build something you can buy cheaply. Well, I think the T-cell is an interesting illustration there. I can't believe the complexity that people go to with their T-cell for what is basically a simple flashing LED. The last comment I'll make before I move to the next slide is this. If when you're bringing the car together, or when you're testing, as I said, partial systems, if something doesn't work, don't keep going. There's a real tendency to say, oh, yeah, well, it stopped once, but I don't quite know why, but I don't have time to figure it out. So I'll just keep going, and I'll keep developing on software in particular without understanding what the fundamental reason is as to why it stopped or why something isn't working. I can virtually guarantee if you go down that path, particularly with electrical microprocessor software type stuff, whatever caused that initial failure will come back and bite you, probably during endurance. So you have to really stop yourself and say, if something didn't behave like I expected it to behave, I need to find out why now. Because particularly at the early stages, when you're building from the bottom up, if you've got something not quite right down the bottom, and you don't find out about it until 2 months later, you have to start again in the build up from the ground up process. And that takes a huge amount of time, and it's very disheartening. The message is, if something doesn't work as you expect, stop and say, why not? And again, that's the strategy that I use with my company all the time. The guys and I have learned over the years that if something doesn't work right, you stop and you say, there must be something not quite as we expected. Let's find out why. So there's a kind of a process of thinking about what you're doing, keeping track of time and keeping control in a management sense of where people are going, and looking out for delays and trying to catch them before they become mission critical delays. I think that's, by the way, how NASA got to the moon. And I think it's also part of the reason why NASA managed to blow up a couple of shuttles. They changed attitude and philosophy from one time period to another. All right, next slide, Nick.
Yep. Come on, slides. We're getting there. Here we go.
Right. No, you went back again.
Yeah. Yeah.
Okay. Now, there's a couple of questions, but I'm happy to take more. What electrical data is most important to gather, monitor, optimize? Well, I'm going to give you a simple answer to that. What do you need to know as to why the car stopped? Because that's the data you need to gather. Do you really need to gather how good the torque control was? Do you really need to gather how good the optimization of your current regulator is? It's nice, but it's not important. What is important to illustrate is, why did your shutdown circuit stop unexpectedly. And that's, by the way, our most recent experience, again with RMIT, and the shutdown circuit just decided to stop. And they had all sorts of criteria about what might have gone wrong. And I said, well, did you hit the car with a hammer? And you might say, well, why on earth did I think that? Because that's what happens on the track. And guess what? They hit the car with a hammer and the shutdown circuit stopped again. Well, there's a bit of a clue. Something is reacting to vibration. And so I said, okay, how are we going to know which part of the shutdown circuit stops? Oh, we'll put a data logger in. I said, how about we just build a board full of LEDs? And we have a LED that comes on when any particular switch in the shutdown circuit comes on. And they said, oh, I suppose we could do that, but it's not nearly as much fun as a data logger. And I said, yeah, but it'll work. So the electrical data you need to gather that's most important is what has stopped the car. After that, you can start to look at what your optimizing performance is, but that's not so important. Well, I know what the cooling the batteries. We can talk about that with questions and answers. So the electrical accumulator design is something I prefer to handle with questions and answers. It's a variable process. And the last question is the accumulator itself. Now, this is something that we are on the committee consistently concerned about. First thing I recommend all teams with an EV do is go and find the video that talks about how lithium batteries catch fire. It's very salutary because it'll tell you what you're dealing with. You're dealing with essentially a relatively unexploded bomb. The advice for the RMIT students whilst I was in charge, and I hope it's still the advice, is if anything happens in the lab, what's your first job? Get out. Not to attempt to put the fire out, not anything else. The answer is get out of the lab if anything goes wrong seriously, because that way you'll be safe, and then all we've got to worry about is the fire brigade.
Yeah, I'm just like on a Teams meeting thing, which I... No, it's not important. It's just like a webinar.
Yeah, it is a webinar. Like... could you just turn your mic on mute, please? Thank you.
Yeah. So, given that, you then have to stop and say, every time I work on a battery, I have to be aware of what's going on, and that means safe working practices. In other words, you work on the battery in segments. You design your battery so that you can segment it readily and work on each part. You design it so if you wish to charge it or discharge it, that's not a casual process. It's not like getting a Ryobi battery and plugging it into a Ryobi charger. It's a proper process that needs to be managed. You need to organise how you're going to do it, where you're going to do it, and who's going to be the responsible person in charge. And probably you need a hierarchy of process so that if you are working on substantial parts of the battery, in or outside of the car, you've got a accredited person in charge. That's the way that electrical people work in the overhead wires when they go and service the wires down the street. And sometimes if you watch the guys from United Energy or whatever in their cherry picker working on the overhead wires, you'll find that there's somebody who apparently is just standing around. And if you look carefully, he's the guy in charge. And his job is not to get involved in what he's doing. His job is to watch what everyone else is doing. And should he see something he's not happy with, he can pull the plug on the spot. That's a nice, safe way to work with these batteries. And as a team organisation management process, that's a good idea. What should you test? Well, you should test that you can charge, you could discharge, you should test that your BMS works. And that should all be running safely before it goes in the car. One of the biggest improvements at RMIT is that these days they build a virtual electrical system on the bench. Now, virtual electrical system, what do we mean? We mean all of the electronic components and the wiring loom and the motor and the battery all constructed with wiring that's about the same length as the wiring loom in the car, physically arranged similarly, using exactly the same connections, such that in practice you could actually pick up their test version of the electrical system, put it in the car, and it would work. And sometimes they do that in 1 year. Now, what's the benefit of that? Well, it means you don't forget anything. It means all of your connections have been thoroughly tested and rechecked. It means that you're running the accumulator and the charging and the battery similar to how you run it in the car at the race competition. And you've done all of those things how long before? 6 months would be nice if you could do it. So that's the reality of doing this. Keep the timelines going. Recognize that the electrical and mechanical and indeed the software timelines work differently, and accommodate that. The guys managing and coordinating the team have to keep track of these significant variations, but they also have to have a capacity to look out for the people working on one black part of the black box to slip and keep saying, oh, I'll get it done tomorrow. I'll get it done tomorrow. And as I said repeatedly, and I'll say it again, most EV cars stop at the competition because of something really simple. So that's what you've got to try and fix and find before you get there. And that'll probably do me.
All right. Thank you, Nick, and thank you, Graham. Fantastic. I've heard this all before, and I'm still pinned to the computer. I'm learning something new every time. Good storytelling. Thanks, guys. Now, as we said at the beginning, a couple of things. We have until 8 o'clock. We don't need to use all that time. We're going to take some questions in a minute, but before I do, I did note there's a couple of names here I saw. One was Nathan Tarlington, the clerk of the course, and one was David Ford, the rules chairman. Do you guys want to add any comments before we go to Q&A, or should we go straight into Q&A? It's up to you.
I'm good with going to Q&A.
Thanks.
Yeah.
Thanks, Nathan.
I just add one added bit reinforcing both what Nick and Graham have said, and that is the requirement to establish a proper project timeline. If you haven't done that at the start of the year, you'll never get to the end properly. And it may now be too late this year, but you should establish a project timeline with clear dates all the way through that process as you're going down the V and up the other side of it. All those dates should be listed out and met. And also it should be realistically based. If you have a car, which when you lay it all out, you realize you cannot achieve it within that timeline, you then have to either decide, all right, this will be a 2-year program, or B, we will have to cut back what we're going to design and validate to a level which can be achieved within the timeline. And you must meet those dates. Letting anything drift out will mean you won't achieve the testing or the validation, and you will never get to the track. So I just reinforce that stuff relative to timing. And we used to have a thing on the wall in the office of a program I was running, which said the enemy of good is better. And that's very true. So I'll just finish on that.
Just to pick you up on that, David, and I agree with you, you also need to have a timeline management capability such that when, as often happens, a particular part can't be met for various reasons, you can pivot and redesign your timeline in a dynamic way rather than saying, oh, well, I'll let the rest of it sit there. In other words, one of the things that happens is that if something doesn't work properly, they just push out the end date for that, but don't go and then follow through the implication on everything else. And then you lose sight of the fact that you've created Mission Impossible. So your management of your timeline is a dynamic process, not a static process at the start of the year.
Yeah,
and just,
I agree totally.
Just a little bit of clarity. David Ford used to work for Ford, and I used to work for Holden. And we had a similar sort of philosophy, which was it's time to shoot the engineer and start production. And what that meant was any engineer worth his salt will always think he's got one more iteration to go and it'll be perfect. And it never is. It's time to stop designing it, stop engineering it, and get on with the rest of the stuff which you heard tonight. So yeah, Ford and Holden were in sync with a lot of things, and that's one of them. So another thing I want to make out before we go to Q&A is that what you've heard tonight is not theoretical. Every single organisation that has a engineering department follows this process. Well, everyone who's successful, because it is reality. It is what you have to do in order to get to that end product, the end outcome, which is in our cases was production of a vehicle, but it could be production of anything. So no, this is not theoretical. That's real stuff. Now, enough. I welcome anybody, and I guess the best way you can raise your hand, or you can simply come off mute and ask any questions of anyone. Please feel free.
You got a hand up there, Adrian?
Hugh Simpson.
You're on mute, Hugh.
G'day. Thanks, everyone. I'd just love to hear anyone's or Graham's insight into answering those two questions, the cooling batteries and also the cell arrangement as well. That'd be great. Thank you.
Okay. Cooling the batteries is a really challenging one. It's a question of air versus water cooling. If you're going to put air in and you don't want to get water in, you have to create a water baffle. And usually you do that by putting air through an up-down arrangement whereby if water comes in, it a bit like an oil filter, it'll go down a baffle and then drain out the bottom. The trouble with air cooling is that you've still got to get the air through the batteries. And that's really hard. The problem with water cooling is that you've got to have a water fin between all of the battery cells, and that's very hard to manufacture and usually makes it larger. RMIT over the years has tried all of those approaches, and I don't think there's a best one around. If you go to Tesla and the EV cars, they're not so worried about weight, so they tend to put water down thin tubing in between the batteries, which is a really good solution, but it's expensive and it requires very complicated engineering to make it work. The best approach that we've used at RMIT was to put effectively a thermoconductive gel between the sacks, and then that gel it would phase change as it got hot, and that absorbed a lot of energy. And secondly, you could make contact with cooling plates either side of the gel and extract out some of the heat. But what they did with that design was quite clever. They didn't plan to run the battery continuously forever. They worked out the amount of energy that was in the phase change of the gel and said, okay, that'll give us about 45 minutes running. And that got them through endurance. And so they knew how much heat loss they were trying to deal with, and so they could design it. But there's a further question comes out of this. Before you can decide to cool your battery, how much heat are you trying to extract? And people often lose sight of that question. Like the classic has been, again, RMIT. Every year they've had the water cooling radiator for the engine, not the battery, but it's similar. And it's a fantastic bit of cooling design where they build a radiator and they pump fluid round. And every time I've said, how much heat are you trying to extract out that warrants that size radiator? And since it was designed by the mechanical engineers, the answer is they don't know. So they just picked a figure and said, we'll make the radiator twice that size, and it was well oversized, in my opinion. Now, following that line through, how do you find out how much heat you need to extract? Well, the answer is you get a cell and you test it, or you make up a small pack of cell and you test it, and you put it in adiabatic box, a heat box, and you see how hot it gets when you run it for half an hour. And everyone says, I haven't got one of those. My answer is you do. Go and buy a foam cool chest, because you'll find those cool chests that they use for caravans and hiking are pretty good heat boxes. And so you put a thermal probe in that and you'll know how much heat it's gone up. You can get the resistance and you can do the calculation. Our experience is the resistance from the battery manufacturers is marginal. But you do some tests. First thing, how much heat do you need to cool? Then you can turn around and figure out how to cool the batteries. Now, the question of industry professionals cooling their batteries, remember their target is quite different. Their target is to keep their batteries cool for product which will be used for extended periods of time by the uninformed public. That's not your goal. Your goal is to build a battery that will keep it sufficiently cool whilst you're running for 45 minutes around endurance. Different question. You're still not sure? Go and build a system and test it and see. I mean, you need an ability to load a battery up for half an hour and then put your cooling system to task, which means, of course, you need to measure the temperature, which means you need to have your BMS running. So it cascades on. Optimal ways to arrange the cells when designing with accumulator containers. Ooh. Well, in my view, you start by picking the pouch that gives you the energy that you need to get your car around the track. Again, you're not designing it for continuous running, you design it for 45 minutes. One of the best designs we ever saw one year was the team from Munich. And they came along with a battery size that was about half the size of anyone else. It was a beautiful piece of engineering, but it didn't have enough energy to get them round because they had regeneration. So they'd done their numbers and they said, we only need half the energy because we can get most of it back from regeneration. Were they correct? Yeah, they won the competition hands down. So they were using the cylindrical cells. So the optimal way to arrange the cells, I think, starts with what cells can you get. You've got a choice of the cylindrical ones or the pouch ones, but really what you're looking for is an arrangement of cells which will give you the right voltage and the right energy to get your car around the track. Then you can start to think about putting it together mechanically, and I'd probably be putting thermal before I talked about structural as the mechanical problem, because you can always wrap a mechanical housing round once you've decided how to mount them.
Graham, before we SJ's got a question. Before we move to him, a supplementary question for me. You want to comment on the value of using last year's car as a test mule for this year's car?
I have mixed feelings about that, Adrian. I think it'd be very sensible, but somehow the teams don't seem to want to do it, and I don't quite understand. It's a really good driver training one. I mean, it has, well, there's some obvious benefits. If you can keep last year's car running, given that this year's car is probably not coming together until August, September, maybe even October, you can train your drivers ahead of time. I know for a fact last year that one particular team went into skid pan where the drivers had never done a skid pan. That was their first time around the loop. They just didn't have time. If you'd had last year's cars running, you would have had time. The trouble is it's expensive, particularly for an EV car, because if you're going to keep last year's car running, you either have to build a new battery pack set, and that's really expensive, or you constrain your design so that you use the same battery pack from last year and you swap it between the two cars. In terms of trying ideas on last year's car for this year's car, it doesn't seem to be particularly successful. What happens is that it's very easy to make changes for the benefit of this year's cars that make the two parts incompatible. I know that RMIT for a while were using the same suspension struts and they would live with that. They've also used the same electronic processor boards because essentially they're much the same functionality and you just need software to change it. So you can get some benefit from the previous year's design, but it doesn't seem to progress particularly well to more than just some parts of last year and a driver training platform.
I might just jump in here as well. This is something I've got a bit of knowledge of, and I think David Ford after me will have a point to make it around here too, is that quite often that we see teams pushing themselves to create a brand new car each year. And a couple of times in this presentation, this webinar, we've spoken about the 2-year program, and we're really looking into how teams utilize that same vehicle in the second year. If you think about a 2-year program of reusing your first year's car in the second year, well, that's in the second year, you're optimizing your parts. You're not building a whole new car. And that's a way that you can still learn, you still can engineer, but your focus is not building something from scratch. It's about optimizing the parts and getting the most out of your design. I think, David, you might have some practical experience on that.
Yeah, just before David chimes in, just to pick up on that, Nick, I agree with you. But the other side of the coin that I tried to get them to do, but it's never seemed to happen, is when you want to do a major shift from your car design to the next car design, I don't think it's a good idea to do that in 1 year. And you're better off to say, look, we will build not a second year car, but a similar design car for next year, which should take less resources because there's a whole lot to copy and borrow from. And at the same time, we will keep another development program going so we can get the early development done of that change in the 6 to 12 months before the next competition. Now, I believe that's how Monash operate, and that's all to their credit. And a really obvious one is going from in-vehicle to in-wheel drive. That's a major change. And doing that in 1 year is complicated. And going to a four-wheel drive from an in-vehicle drive in 1 year is doubly complicated. And to me, that sort of development should be phased in over a couple of years whilst you're still competing with a previous version, which isn't as complicated.
Yeah, I agree. David, do you want to talk about some of your experience?
Are you on mute, David?
He's still on mute.
Yeah, on the point of level of change. In fact, in the automotive industry, even though they tout vehicles as all new, they may look all new on the surface, but underneath, most of those vehicles are actually a lot of major carryover of structure, suspension, and that sort of thing. In Ford, particularly in Australia, we tried never to do an all-new body and an all-new powertrain at the same time. We would split between the two. Now, presently the rules in Formula SAE mean you must make certain levels of change with it, but don't try and do everything all new from year to year. And in fact, if you've got a team that's large enough, you can be running some stuff in advance for the next year's car to get a step up on that, rather than trying to do it all from scratch right from the start of the year. We are now looking, I will say, at the rules with the intention for future years of modifying the requirements so they are not so stringent relative to arbitrary changes you must make to the vehicle, which I think will give ability to have a more sensible flow of level of change, which in fact more closely correlates with industry in any event.
SJ, sorry, thanks, David. SJ, you've been waiting for about half an hour, you poor guy.
Sorry, Adrian, just Ricky's just made a comment that, yeah, larger teams can do that way. For smaller teams, it's much harder to do background change from year to year, and I fully agree, Ricky, but, you know, that's life. Okay, SJ.
SJ, have your say.
No, thank you very much. And thank you very much for the webinar. We've learned lots about this. My question is more around, I guess, the competition scoring and points. So I was wondering if there would be any changes to points calculations being released to teams, like even on the granular level, like amount of cones hit during endurance times this many. Was there any changes? Because in previous years, I believe that we haven't received our points breakdown or calculations, I guess, as specific as we'd wanted to in the past.
Look, to be honest,
I think that falls into my bailiwick more than anybody else. Look, in terms of an individual team, then I think we would be willing to provide data on your points deductions from your actual raw measured score in the dynamic events. I will discuss that with our scoring captain. I don't see any major issue with doing that. We would not, of course, provide that data to all teams. We would provide it only to an individual team for their own data, and also say that if you thought the number was different, then then it won't be different. Whatever we have in our records, it will be taken as the exact thing, because some of these cone measurements are fairly subjective at times when teams are looking from the sideline versus what you see out on track. But we'll take that question, and I think it's something we could do.
I don't want to shut this down too soon, but this really is a question not for tonight, but for the teams meeting, because tonight we're really focused on how to compete successfully. This is more about details of how we run the event, and that is the opposite side of the coin. We're really talking about how to help teams be successful. Your question, and I don't want to shut you down or be dismissive of it, but it's probably more appropriate for the teams meeting in August. If you can hang on to that question, we can do a little bit of investigation for you in the meantime, as David said. But I don't want to delve too much into that sort of a question tonight, if we could, please.
I agree
No
with you.
worries. Thank you very much.
Any other questions on tonight's topics?
Somebody's still got a hand up.
Yeah, fire away.
Oops, I just need to take that down. Sorry.
Okay, yeah, hands down.
Well, look, I'm happy to pick up Ricky's point about a small team, and I do understand the difficulty. And I think the consequence is that small teams probably are not going to be able to make seismic changes very often. They will have to do it sometimes, and that may mean that your chances of a podium compared to the larger teams that have the capacity to do that, yeah, but you still be in the top 5 if you finish.
I think also we recognise that there are small teams, good teams, bad teams, new teams, old teams. There's enormous levels of teams, and that's we can't change that. That's the nature of the team structure. We put on an event and we make it happen for the teams, and they have to deal with whatever challenges they have. And we've had this discussion a lot. Like a classic example was when we released the layout of the endurance track many years ago. One for you, Nathan. And there's questions about, but only the big teams are going to be advantaged. Well, the issue was, the reason we did it was to make the whole event safer and have less cone strikes. So yes, some teams will be benefit, some more than others, but the bottom line was our purpose was to make the event safer, and the unintended consequences are what they are, and we can never ever change the dynamics of the different level of teams.
And just a little bit further on that before Nathan jumps in. Like I've been part of a really small team that had really limited resources, right? And my team didn't do particularly well when I was in it over 10 years ago. But in that moment, in that year that I was involved in building that car, I learned the most that I've ever learned, and that's changed the shape of my professional career, right? So don't think of it about trophies and podium places. Think about it about your learning journey, and that's what we're here at SAE to really promote. This is not about building a car, as Graham said. He doesn't even care about cars. It's about engineering and engineering education.
Yep, I would reinforce that, Nick. And we recognise that small teams are at a disadvantage. And because of the educational aspects, which is the prime intent of the whole exercise, we will consider any issues raised by small teams relative to either rules or other items. So if you are a small team, we will give consideration to that, and don't hesitate to ask questions relating to that.
So I think Sumi's got her hand up again, or was Nathan wanting to say something before that?
I would say, I'll probably just reiterate what everyone else has just said on the exact same point. Like one of my last years when I was actually a student doing the same thing, I was part of a team. There was probably 3 of us that turned up probably in the entire year, or, consistently. And that was probably also one of the years that I learnt the most, to a certain degree, through, timeline management, actually being involved in everything. And I guess at the end of the day, that is for the most part, is the point of the competition is to learn and build those sort of structures and become better engineers, business students, whatever you're trying to take it out of it, to get, more equipped for employment in future years. And to that end, like obviously to the same point, we were obviously combustion back then. So to the point of it was obviously easier for keeping a second year car around. From my current role now and sort of being clerk of the course and that, obviously, as Graham was saying earlier, like if you can drive your car around and test, like we were going out twice a week, we'd have an afternoon pegged at our local track that we would have booked in for every week, twice a week. Just go drive the car around. If you have a handle on how the course will be sort of laid out, what a skid pad looks like, driving around cones, and just being comfortable in these cars. Obviously, a cone strike's 2 seconds, an off track's 20 seconds. If a lap's only 60 seconds, these are quite big percentages of time that's going to end up added to your score if you're sort of not comfortable and sort of actually know how to drive these cars. Like one of our teams last year that got lost during endurance and went and joined the North Circuit and had to get parked there. Obviously, if you're sort of comfortable in a car, which you can only really do from miles in these things, really sort of, I guess, from dynamically is a good way to sort of add to your score.
Yeah, actually, you made a point. It's the main point. The whole purpose is the only purpose of this event, from our point of view, or my point of view, is for students to learn, not to get trophies, as David I think referred to. So, don't be confused with what our intention is here. We're not interested in who wins and how many points you get. We're interested in what sort of engineers are coming out of this program. So I just want to, and the whole committee is totally at one with that concept. So I know teams have a different view, and I understand that. Everyone's competitive. Everyone loves to win. Reality is, as Nick said, the whole purpose of this program is to teach you guys to become better graduates. Sumi, I think you got your hand up again. I assume it's purposefully.
Yeah, thanks. Kind of on the earlier conversation about team size and team structure, I guess our team comes from the opposite side of the spectrum where our team is quite large. If I might say like the largest on the paddock, in the paddock. I was wondering what your thoughts were about kind of on the upper end. So for context, we have about, I would say 160 students in our team. And if you've noticed, we probably have around 80 students go to competition. And I was wondering if you thought there may be like an upper limit of how many students we should take on as a team, so as not to, I guess, quote unquote, dilute the work that's available. I just wanted your thoughts on that, kind of a curious question.
I've got views on this. Do they have a purpose, or can they all become system owners? Like, if they don't have a job and if they're not learning, like, there's your cap. But if you can find a way with such a large team to give them purpose and enhance their learning opportunity, why have a cap?
Yeah, I think there's possibly going to be some limit where you can really have meaningful input by those people. And once you get beyond a certain size, I think the breakdown of what is assigned to each member and they understand where they fit into the individual systems breakdown from the total vehicle becomes pretty meaningless if you're the engineer in charge of a screw and that's it. So I think, yeah, there's possibly there. And as Nick said, are you giving them something meaningful to do or not as part of the total effort? And of course, can you manage it? Can you actually oversee that many and the inputs coming in from that many people? And you may want to get to a point and say, right, that's our cutoff. If these other people are interested, then they can be observer team members, shall we call, but they will not probably be actual participating team members in terms of design and development of the vehicle.
It's a very hard question to answer, I think, from our point of view, because we are arm's length from the teams. But I think, David, from an industrial experience point of view, I think what you're saying is that, you can have an organisation that's too big, and the classic, we always used to joke about General Motors Holden, where you'd have a door engineer, but he's only responsible for the front right-hand door. We had a different guy do the left front door, so it wasn't literally that bad, but it seemed that way at times, and I think the beauty of Australian automotive when we had one was that we were lean and mean and very productive, and that was due to the fact that we weren't overstaffed, were at times over challenged, and that's a good thing. So from a team point of view, you have to find out your own level of comfort and what works for you. But I think the short answer is you can be too big, whatever that number is. You can certainly be too big.
So fair. Thank you very much for your input.
Okay. That's an opinion only, and you guys have to sort of work through that. Any other questions? So we're getting close to 7:30, which is a nice time to sort of wrap things up, if we will. One or two more questions, or shall we call it a night? I think I'm sure there's people with places to go to. Hopefully this has been a benefit. I think as I said in the beginning, Nick and Graham nailed it when it came to the presentation. I think you guys would I hope a benefit from that. Ricky, I think I see your hands up, so we'll come to you. But if no one else, we'll move to Ricky, and then we'll see how we go.
Well, yeah, I just wanted to ask whether this recording is going to be available for us to get access to at a later point. I think there was some really valuable information at the start that I'd like to play back to the rest of the team.
Yeah, and that's the whole purpose of having small representation tonight. Was exact. So we'll put the presentation material online, and we'll also put the recording. And obviously, that's the reason why we did the recording, so we could actually share with others who couldn't make it, or there are people that you represent who obviously we couldn't have too many people online. So yes, absolutely, we'll be doing that.
Great, thanks very much.
Adrian, can I just finish off with my final statement? And that is, if there's any requirement or anything that you take away from the presentation tonight, is that this system shell statement. And is that students shall design vehicles that are specifically adaptable to the high vibration surfaces that Calder Park will present to them. That is
okay. That's a caveat. MP.
That's a hint.
Question.
Oh yeah, thank you for the webinar. I'm just wondering, like, I know you said not to do it, and like sometimes it's good to keep things simple. But how would you go about designing like complex systems and complicated systems?
Yeah. Okay. So this is where you apply systems engineering thinking. Yeah. So each complex system can be broken down into a series of systems and systems. So if you think of your system boundary as a big box that contains many systems with complex interactions, you can work through and break down the complex system into a series of simple systems that have really clearly defined inputs and outputs, or a clear system boundary in a very high abstracted way. There's many ways you practically can do that. And I seriously, if you're interested in working this out in a practical way, is having a look at the Systems Engineering Handbook by NASA. You can Google it. It's a free PDF. It's a big textbook, but they've got some very practical ways of how NASA breaks down their big complex problems, like building a rocket to go to Mars or send a satellite out into geostationary orbit. But they break it down into systems and systems and systems. So I think that kind of knowledge could really help you answering that question.
Well, I agree with Nick on that. It's definitely a case you just treat the complex design you're looking at as if it's the same way as you would for a total vehicle, and break it down into the systems, then the subsystems, and from that down to componentry. But in doing that, you need to in fact start off with what's the total boundary of your overall system. Then as you break it down, have a clear boundary around each subsystem, so you know where they are and where they will interface one with the other, and you then go on and break down from there into your lower levels. But always be able to put a context or a boundary around the step you're at in that process.
I'm going to be slightly more negative about that. Yes, the principle of systems and breaking it down into parts is that you can define a clear interface between all of the parts, such that when you build the parts on that definition and bring it all back together, it will operate as a whole. But I'd give that about a 7 out of 10, because my experience is that the amount of time you can spend on trying to define the interface such that it is perfect within it, and then particularly with software, when you start to bring it back together, it just doesn't seem to work. So maintaining a picture of the system as a whole, even as you break down the parts. Remember I said earlier about, I asked my engineers, what don't you know? Well, that's breaking down into the parts so you can deal with that part. But you still have to bring it back together. And my experience is invariably, unfortunately, the systems, particularly with electronic systems and particularly with software, they can interact with each other in ways which the definition just completely didn't pick. So you need to keep a systems perspective even as you go down the individual parts.
Yeah, I'd agree with that, Graham. And the secondary thing is, would you recommend people go complex in design? And the answer comes back to what Graham said earlier, KISS. You're going to probably be far more successful if you don't try to be overcomplicated in your design as you work through the systems there. So keeping it simple is obviously a better way to go if that will achieve your objectives.
Well, your other option is to put the complexity together in a way that if it doesn't successfully work, you've still got a simpler system that'll run.
Yeah, and understanding your risk is a key one here. In fact, I was just earlier today looking at some notes from a course I taught at Swinburne on managing engineering projects, and one of that was the risk element. And risk can be broken down into risks which you can identify and you know what the outcome will be. Risks where you can identify them, you're not sure of the outcome. But as Graham hinted at there, particularly with electrical systems, there are unknown risks with unknown outcomes. And the more complex you make the system, the more of those type of risks you actually create.
Particularly with the lesser experience of students. If you want a more complicated system, get someone with more experience.
If you go back to the message that Nick started with, the question you have to be asked, why do you want to have such a complicated system in the first place? What are you trying to achieve by having that system? Is it necessary? Can you make it simpler? Why? So, yeah, I think the message tonight is have a real think about those sorts of things before you embark on something which is super complicated and doesn't give you what you really want to achieve. So I'm hoping that the message tonight has been the system engineering has a very well structured, well tried system, and I think Nick explained it very well as to how you approach it, why you do it, and the benefits of not going off track and doing things unnecessarily complicated just for the fun of it. Correct, Nick?
Correct.
Okay, we're going to wrap it up, I think. I'm hoping that this has been interesting. I'm hoping we've answered the questions. As I said, we will put everything online and you can access it and share it and all sorts of stuff. It is free. Don't worry about that. We're not going to charge you for it. And again, thanks, everyone. Thanks for the committee members who supported us tonight. Thanks for the team members who came on and participated. And as we always say, good luck with your project this year. We look forward to seeing you later. But as I also said, we do have a Teams meeting in August to talk more about this year's competition. But I certainly hope that this has been a benefit tonight.
Okay. Good night, everyone.
Thanks, everyone.